Welcome to the Dev Journal, where we explore how artificial intelligence agents are moving from simple chatbots to independent actors with real agency, while nations scramble to secure the Model Context Protocol and invest in national supercomputing, like the $2 billion plan recently unveiled in Canada. Today, we examine the thin ice these agents are walking on after a recent audit found 41% of the servers using the Model Context Protocol are completely wide open, while developers are simultaneously building machine-first websites to detect and filter out unwanted crawlers in real time.
Sloan, I am tracking the audio side of this evolution where agents are finally getting dedicated speech tools like a new 17-megabyte engine that is actually outperforming human graders for pronunciation accuracy, while fundamentally changing how we value acoustic data and cost efficiency in production pipelines.
Vance, that specific focus on precision, reflects the urgency we see across the broader deployment landscape, where the infrastructure of the future is being built today, even as we begin with a vulnerability report, shaking up the foundations of the Model Context Protocol ecosystem right now. The scale of this security audit from Kai Security Artificial Intelligence is truly alarming for anyone following the space. They looked at 518 servers in the Model Context Protocol registry and found that 214 lacked any protocol-level authentication. That is 41% of the ecosystem, essentially wide open for anyone to probe. Looking closer at the impact, the Bitrise continuous integration and continuous deployment platform is exposing 67 sensitive tools for unauthenticated discovery. This includes dangerous commands like delete app and register secure shell key. It turns a simple list into a roadmap for a potential system-wide disaster that any automated agent could find and exploit. We are also seeing specific failures where full execution is possible without any credentials. For instance, Supabase edge functions were found misconfigured with anonymous keys. Instead of just seeing what tools exist, a bad actor could actually run them, turning a mapping exercise into a direct breach of the entire functional infrastructure for those organizations. The velocity of this rollout reveals where the structural integrity begins to fail under pressure. The registry expanded from 90 to 518 servers in a single month as of February 2026. When growth moves that fast, security becomes an afterthought, and you end up with hundreds of unhardened tools being deployed.
Sloan, focusing purely on discovery, we see it allows malicious agents to map entire attack surfaces for free. Even if execution is blocked at the final step, knowing the exact schema of a tool allows an attacker to craft a targeted prompt. They are essentially getting a detailed blueprint of the house before they even start. The hosting data shows that the environment often dictates the security posture, regardless of developer intent. Cloudflare workers are showing much higher authentication rates compared to platforms like Railway.app, Render.com, and Versal. It suggests that the default configurations of these hosting providers are playing a massive role in whether these servers remain exposed. We cannot ignore that social media servers like Sendit are allowing the enumeration of 131 different tools without any credentials. While execution might require an application programming interface layer check, the sheer volume of metadata being leaked gives attackers a massive head start. It is a fundamental failure of the principle of least privilege. This pattern of lazy implementation creates a dangerous playground for bad actors looking for the path of least resistance. It forces us to bridge from these protocol-level vulnerabilities to the outright malicious code flooding agent marketplaces. We need to look at that specific dumpster fire in the weekly security review coming up next.
The situation at ClawHub is a nightmare for anyone building with autonomous tools right now. Koi Security just flagged 1,184 malicious skills designed specifically to deceive artificial intelligence agents. These are not just bugs, but active traps that trick agents into executing remote bash scripts, potentially handing over full control of a system. This lack of oversight extends deep into the infrastructure, where we usually expect the strongest protection. A 2025 analysis revealed that 100% of 16 identified container escapes happened within runtimes and orchestrators. The Linux kernel is holding up, but the very systems we use to manage and deploy these agents are structurally failing under pressure. We are even seeing sophisticated attempts to mask these intrusions by blending in with the noise of modern workflows. Researchers at Checkpoint demonstrated using WebView 2 in 2026 to hide command and control traffic by tucking malicious data inside legitimate artificial intelligence application programming interface calls. They move through a network without triggering any traditional alarms. The psychological impact of these breaches is massive because it erodes the basic trust we place in these automated ecosystems. We are essentially handing the keys to our digital kingdoms to agents that cannot tell a helpful skill from a lethal trap. Vance, does the underlying code for these marketplace skills offer any clues about how we reach this point?
When you look at the SNIKE scans of the OpenClaw marketplace, the negligence is staggering. They found that 7.1% of all skills actually expose credentials in plain text right there in the source. It is a fundamental supply chain failure, where developers are prioritizing ease of use over basic secrets management, leaving the front door unlocked for anyone. Fragility in the ecosystem explains why core infrastructure providers like Treefic are scrambling to patch critical vulnerabilities in their edge routers. They just released updates for versions 3.6.8 and 2.11.37 to address dangerous mutual transport layer security bypasses. These flaws allow attackers to bypass identity checks or crash the entire system. Automated attack vectors are making traditional defenses look hopelessly obsolete. This shift drives the 2026 recommendation to move away from time-based one-time passwords in favor of hardware keys. Real-time phishing proxies are so commoditized that any software-based multi-factor authentication is now a liability for securing high-value technical environments and sensitive data. We must start viewing the web as a hostile environment where every visitor might be a malicious bot instead of a human. This realization forces a complete rethink of how we build for the modern internet. Let us pivot from defending against malicious agents to how we intentionally design web architecture to handle autonomous crawlers in the next segment.
Engineer Daniel Shively is taking a proactive approach to this hostile web by launching Echo Atlas. This specialized website is designed specifically to observe and classify autonomous agent behavior in real time. Instead of just blocking every crawler that hits the server, he is treating them as a new class of digital citizen with specific needs. One of the most fascinating features is the use of cognitive honeypots. These use inference-sensitive semantic constructs to measure how consistently an agent can reason. By analyzing these patterns, Shively can actually track how often different models succumb to hallucination when they interact with the site architecture, providing a rare window into their internal logic. When the system identifies an agent, it redirects them to a dedicated application programming interface endpoint. This path returns structured JavaScript object notation with explicit schemas and topic metadata. It is a machine-first routing strategy that prioritizes giving these artificial intelligence visitors the clean data they actually need, rather than the messy hypertext markup language humans prefer. This shift from defensive blocking to intentional data delivery feels like a more sustainable way to manage the rising tide of autonomous traffic. It turns a conflict into a collaboration where the infrastructure adapts to the visitor. Vance, how does the system actually distinguish a sophisticated artificial intelligence agent from a standard browser during that initial handshake?
That diagnostic process is surprisingly granular. The heavy lifting happens through a probabilistic detection model that ignores the easily faked strings we usually rely on. It analyzes header shape anomalies and the specific ways an entity accesses the robot's .text file. By looking at these signatures, the system can spot a crawler masquerading as a human. Beyond just spotting the agents, The way the system serves data is the real differentiator. Providing that deterministic formatting at the endpoint is a brilliant way to solve the scraping problem. By serving structured data, you eliminate the interpretation errors that occur when an artificial intelligence tries to parse complex visual layouts meant for human eyes. The visibility this creates for developers is substantial, but I am particularly interested in how they handle the privacy side. The telemetry model logs hashed Internet Protocol fingerprints and sanitized headers. This allows the system to track behavior at scale across thousands of interactions without harvesting any personal data while maintaining a hard line on security. We are moving from general web layer agent interaction to the highly optimized, specialized application programming interfaces these agents require for complex tasks. This evolution is especially clear when we look at how specialized engines are now handling human speech. Our next topic explores a tiny engine that is outperforming human experts in the field of pronunciation scoring.
Fabio Augusto Suizu has developed a 17-megabyte pronunciation assessment engine that is 70 times smaller than the 1.2 gigabyte academic standard models. This drastic reduction in size allows for sophisticated linguistic tools to reach 1.5 billion English learners across the globe without requiring massive hardware. The business case for this miniaturization becomes clear when looking at cloud deployment costs. The system enables serverless cold start times of under 2 seconds. In contrast, standard academic models often take over 10 seconds to initialize, which creates a frustrating delay for any student trying to practice their speaking skills. By optimizing for standard central processing units, the architecture ensures real-time feedback is accessible to everyone regardless of their device power. It creates a seamless user experience that previously required expensive dedicated servers. Vance, what do the raw performance numbers say about the quality of the scoring when the engine is this small?
The metrics reveal a very high level of precision despite the tiny footprint. This model achieves a sentence-level Pearson correlation coefficient of 0.710. That actually outperforms the human inter-annotator agreement benchmark of 0.675, meaning the software is more consistent than human experts. We do see a specific trade-off regarding absolute peak accuracy compared to the largest cloud providers. This model gives up approximately 10 to 15% relative accuracy for its massive size reduction. For example, Microsoft Azure maintains a higher phone-level Pearson correlation coefficient of 0.656 for its users. However, the speed advantage is undeniable for interactive applications. The median inference latency is measured at just 257 milliseconds. This is significantly faster than the 700 milliseconds observed for Azure Speech, allowing for immediate feedback that keeps a learner engaged without any perceptible lag or processing delay. It is impressive to see a 17-megabyte file outperforming human benchmarks while maintaining such low latency on basic hardware. This efficiency demonstrates that we do not always need massive neural networks to achieve expert-level results in specialized domains. The focus is shifting from general capacity toward extreme task-specific optimization. This high level of performance for specific tasks is why autonomous agents are currently abandoning general-purpose large language models for specialized speech application programming interfaces. These narrow tools offer the acoustic accuracy and cost efficiency required for global scale. Next, we look at the specific economic factors driving this massive architectural shift.
Artificial intelligence agents are struggling with the lag inherent in general-purpose models. While a standard large language model takes approximately 8 seconds for text token inference, these specialized speech application programming interfaces slash that time down to just 257 milliseconds. It transforms a clunky interaction into a natural conversation. The technical reason for this speed is how the data is processed. Large language models are designed for text tokens, which means they fundamentally lack the ability to generate phoneme-level data or word-level timestamps. By working with raw audio waveforms directly, these specialized tools provide a level of acoustic detail that general models simply cannot match. We are seeing these capabilities integrated into the developer workflow through the Model Context Protocol. This protocol allows the pronunciation assessment tool to function seamlessly across major platforms like Claude Desktop, Cursor, and Windsurf. It is no longer a niche feature, but a standard component for any sophisticated agent aiming for true linguistic precision. This architectural choice is not just about the technical fidelity of the speech, but also the extreme efficiency required to run these systems at scale. Vance, when you look at the economics of running these agents across millions of users, do the savings from moving away from native audio generation justify the complexity?
The economic argument is actually the strongest part of this shift. Running a single pronunciation assessment on a model like Opus 4.6 costs approximately 15 cents. In contrast, moving that specific workload to a dedicated speech application programming interface drops the price to just 2 cents per assessment. That is a massive margin improvement. From an engineering standpoint, these specialized speech-to-text interfaces offer granular data that native audio pipelines currently lack. We get per-word confidence metrics and quality data that allow the agent to pinpoint precisely where a speaker is struggling. Without these specific metrics, an agent is essentially flying blind when it comes to subtle acoustic nuances. We are also optimizing the output side using compact 115 megabyte text-to-speech models. This approach avoids the high output token costs typically associated with native audio generation in large language models. By keeping the models small and specialized, we achieve much higher acoustic accuracy while keeping the operational overhead manageable for global deployments. While these specialized tools solve the immediate execution problems for developers, they also highlight a broader trend in how computing resources are being allocated. We need to pivot from technical execution and agent optimization to the macro financial forces driving artificial intelligence infrastructure at the nation-state level, as countries seek to secure their own technological sovereignty.
Transitioning from agent optimization to the massive scale of national infrastructure, the United Kingdom is leading the charge with a £500 million sovereign artificial intelligence unit established in July 2025. This is about more than just technology. It is a calculated move to secure global influence over frontier development. Not to be outdone, Canada has committed $2 billion over the next 5 years to build its own public supercomputing infrastructure. We are seeing a fundamental shift where nations no longer want to rely on foreign cloud providers. They are treating compute capacity as a critical utility, much like electricity or water. This trend is manifesting in the public sector through massive partnerships like the one between France and Germany. They are working with Mistral Artificial Intelligence and SAP to deploy a sovereign native enterprise resource planning system by 2026. It is a strategic effort to digitize public administration without sacrificing data privacy for millions of citizens. Even defense sectors are pivoting toward this localized approach to security. The Australian 2025 policy for the responsible use of artificial intelligence now permits defense agencies to use sovereign handling for sensitive intelligence data. Vance, does the private sector investment scale make these government initiatives look like a drop in the ocean?
While those public funds are significant, the private sector in the United States is operating on an entirely different level of magnitude. In 2024 alone, private American firms invested $109 billion into artificial intelligence. That is approximately 12 times the amount invested by China during that same 12-month period. Beyond the raw capital, the regulatory environment is forcing a technical migration towards self-hosted systems. The European Union Artificial Intelligence Act mandates strict oversight for high-risk systems, which is driving organizations away from black box models. Developers are increasingly turning to local inference architectures to ensure compliance while maintaining full operational control. The reality of running these models on local hardware is often far more difficult than the policy papers suggest. Operating with under 16 gigabytes of video random access memory forces engineers to use extreme quantization methods like GGUF. Without this specific optimization, these sovereign systems simply cannot maintain the performance needed for real-world use. These technical constraints are ultimately redefining how nations approach their digital borders. As sovereign data handling policies become the standard, we are seeing a total transformation in global technology procurement. Governments are no longer just buying software. They are building the specialized infrastructure required to protect their technological sovereignty in an increasingly fragmented world. Seeing 41% of Model Context Protocol servers operating without any authentication is a wake-up call for anyone building autonomous agents. We are layering sovereign infrastructure on top of a security landscape that already looks like the OpenClaw dumpster fire. The engineering reality simply has not caught up with the national ambitions we discussed earlier.
Vance, those vulnerabilities highlight why the scramble for control is so desperate right now. As these agents become truly autonomous actors, the industry is forced to reconcile $2 billion supercomputing strategies with the basic reality of unauthenticated servers. We are trying to build a fortress for national data, while the front gate is still wide open. The race for sovereign intelligence is not just about who has the fastest hardware or the most capital. It is about whether we can trust the autonomous systems we are deploying into our critical infrastructure. Thank you for joining us as we track these shifts in the technical landscape. We will return tomorrow with more from the Developer Journal.